In lecture, we're not going to see the entire implementation of what a heap might look like, but let's get some insight, and in Lab 9, you'll get a chance to do it yourself. So the first thing I'm going to do is talk about general approaches to implementing trees in Java or in other programming languages. So approach 1A is going to be the most natural thing. Imagine I have a tree, which has W as the root, and X, Y, and Z as its children. So there's many ways we could represent this tree, but the most natural approach is something like what you've done in the past. This first approach, tree 1A, in this approach, which is a naked recursive tree, we have a key, with a key memory box called K, and then we have 3 memory boxes for the left, middle, and right child. So in this case, if we look at this diagram, we have W, a left memory box that points at the left subtree, a middle memory box that points at the middle subtree, and a right memory box that points at the right subtree, and that right there gives us a tree. Now you might say, Josh, aren't we talking about heaps? Why do we have a 3-way tree all of a sudden? Well, the goal here is simply to say there are many ways to represent trees, not just the way you've done it in the past. Now this is the approach you used with BST maps, you probably used in the past, but there are other ways we can do this. So let me show an alternate approach. I'll call this tree 1B. In tree 1B, by contrast, we have, instead of a set of links directly to our children, like hardwired links, we instead have a memory box that stores the location of an array of links to children. So here we have our 2 instance variables are key K, and we have tree 1B, which is going to be an array of tree 1B children. So this memory box gives us a link to an array of children. So this approach, well, what's good about it? It lets us, in theory, have an array of however many children we want. We could have some kind of heterogeneous tree where some of the nodes have like 8 children and some have 2, and that will give us more flexibility. But the downside is that our code will be a little more awkward, and our performance will be a little worse, because to get to a child, we have to follow 2 links instead of just 1 link. Now, yet another stranger approach is what I'll call approach 1C. In this approach, we notice that W has 2 memory boxes, one that points to one of its children and the other is null. X, its leftmost child, it has a pointer off to whoever its child is, and also has a pointer to its sibling Y. And then Y has a similar deal where it points at its sibling Z, and so we end up with this tree, which I call a sibling tree. So this sibling tree approach is another way that we can have heterogeneous trees, a little different than what we had before. And this approach, you might figure, well, let's maybe think of what the instance variables are. So we have this first link, which seems to be to a child, and the other one that's to a sibling. And so maybe we'll call this one, we got to think of an instance variable name. I picked favorite kid, or favorite child. Okay? So that's what our instance variables look like. And this also works. So all 3 of these approaches are pretty natural, right? They all give us some mapping from our node to our children. We store explicit references to who is below us. Now, there's actually more exotic approaches where we don't store explicit references, and we've actually already seen one of those when we did the disjoint sets data structure. So in this case, we'll call this approach 2. In approach 2, we'll store our keys in an array, and we'll also store an array of parent IDs. So for example, here again we have the exact same tree. W has 3 children, X, Y, and Z. And so we have a keys array, which consists of W, then X, then Y, then Z. And we have a parents array, where the 0th entry of that array is, well, it says what the parent of 0 is. So 0's parent is 0, meaning W is the root. And 1, 2, and 3 also have parent 0, meaning they're all children of W. Now that's a pretty boring tree, so I've got a more complicated one at the bottom. In this case, I've got a complete tree that looks like K, E, V, B, G, P, Y, A, D, F, J, and so forth. And so my keys array is K, E, V, B, G, P, Y. And my parents array is, well, in this case, we say, okay, well, who's 3's parent? 3's parent is 1, and 1's parent is 0. 12's parent is 5, 5's parent is 2, 2's parent is 0. So 12's parent is 5, 5's parent is 2, 2's parent is 0. And so this is one way to represent this tree. Now, this is not the only way. I mean, we could scramble these in some order and change all the parents to match. But if we store the keys in the order shown and the tree is complete, it turns out that we'll always have this property that the parents array is extremely boring. It will always go 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Okay. So in approach 3, which will be our strangest approach, and maybe if you're not following, pause the video and make sure this really makes sense, because it's about to take a strange leap. Okay? So this is just like what we did with disjoint sets. And so approach 3 is to recognize that if we're storing a complete tree and we store the keys in the order, just reading it top to bottom, which is also known as the level order, by the way. In that case, we could actually discard the parents array completely. And in this case, the keys array is exactly as before, and this will only work for complete trees, right? Because the whole idea here is if we assume that the tree is complete, then the parents array is actually redundant, and so we could ignore it. Okay, so tree 3 is a nicer approach where our tree is represented as an array. Okay, so it seems a little crazy, right? That you can take a structure which is not at all one-dimensional, right? A tree is you have this whole hierarchical structure, but instead we reduced it to this flat line, right? It's kind of amazing, right? I think it's very clever. Okay. So to make sure that all makes sense, I have a little puzzle for you here. I want you to write the parent k method for this code. Now, what is this code? This code actually shows what swim would look like in the implementation of a heap. So if I want to swim in my tree the kth item, so let's say I want to swim this p here in location 5, then I'll say, okay, well, if the element of the keys array in the parent position, so the parent of k, parent of 5 is 2, then what we'll do is we'll say this number is, if v is greater than keys 5, then we would swap 2 and 5, and then we would call swim on this parent. So your job now is to try and write this parent method. It's going to be really short. It's going to take as input an integer, and it's going to return an integer corresponding to the parent. So for 5, it should return 2. For 13, it should return 6, and so forth. So I'll give you guys a short time to think about that, and I will spoil it in the next little bit. Okay. So what I came up with, and what's the answer, is if we subtract 1 and divide by 2, this is the easiest way to do it. Now you could do it with some kind of if statements, but this takes advantage of the way that Java rounds down integer division. So for example, if I do 5 minus 1, that's 4, divide by 2, I get 2. And if I have 6 minus 1, I get 5, and 5 divided by 2 is 2.5, and that gets rounded down to 2. Likewise, anywhere else, the key insight is to realize that for every node, there is exactly 2 children. So for 4, it's 9 and 10. For 2, it's 5 and 6. For 6, it's 13 and 14. And so parent should always work properly. And so we check for 1. So 1 minus 1 is 0 divided by 2, and that gives me 0. There's actually one tiny bug here, which is that if we take, actually let's check and see if it's a bug. If we take 0, subtract 1, we get minus 1, divided by 2, that's minus 0.5. I actually don't know if it works for 0, but I'll leave it as an exercise to the reader. Just kind of a funny thing I thought about. Okay, because ideally the parent of 0 should also be 0, and so my knowledge of Java is lacking to know. But we can look it up later. I won't do it now. So to summarize all those representations, right? We have 1A, 1B, and 1C. Those are all pretty standard. 2 was a little stranger, but we saw it with disjoint sets. And 3 takes advantage of the fact that our tree is actually complete. And this is typically what's done in real-life heap implementations. Because it's going to be very fast, we don't have to follow any links. And 2, the code actually ends up being quite simple, a little strange maybe, but certainly quite simple.